So Evangelia is an electronic energy engineer here at CERN in the beams department. She leads the renovation of the accelerator timing system, leveraging on the White Rabbit technology. Eva chairs the CERN-wide EDA committee, which shapes the strategy direction for electronics design tools. She's a strong advocate for open source solutions in engineering and research.
So welcome from my side too. We're very happy to have you here for the second edition of the FPGA Developers Forum, and I hope we all make the most out of it. I'm Eva Gousiou, electronics engineer at the beams department here at CERN, and I would like to give you a short introduction to CERN, explain where we use FPGAs here, and provide some context for why we felt the need to create such forum. So for those of you that are physicists here, I will probably say something too oversimplified, but bear with me. So CERN's mission is to study the elementary building blocks of matter and the forces that control them. So what we want is to actually look further and further inside matter. CERN started as a nuclear institute, and this is where the N of CERN, of the CERN acronym comes from, because at that time, so some 70 years ago, we were looking inside the nucleus. Today, this is common knowledge, so the constituents of the nucleus are well known. And what the physicists are trying to do now is to understand how the fundamental particles that constitute the nucleus work and how they came to be. And this means actually looking back to how matter was created at the beginning of the universe and how it evolved. There are two branches of physics that are looking at these questions. There are telescopes and particle accelerators. Telescopes explore the remains of the Big Bang, so what was the product of the Big Bang, by looking far away at the cosmos. But there is a limit to what they can actually see. And this is about 380,000 years after the Big Bang. This is when the universe had cooled down and it had become transparent, allowing light to travel through. So telescopes cannot see and they cannot tell us what happened before that. And that is when particle accelerators come in. So they try to recreate the conditions that happened shortly after the Big Bang to understand the structure and the evolution of matter. So by smashing particles together, accelerators can emulate early universe conditions. So in a sense, telescopes and accelerators, they look at the cosmos from two different points of view, and each one offering clues from a different angle. And together, they can help us put together the story of the universe from the smallest particles to the largest galaxies. And at CERN, we are digging deep into the story of the universe, and we are tackling some of the biggest unanswered questions. So for example, the matter and antimatter asymmetry. So for reasons that nobody understands yet, the early universe had a tiny imbalance between matter and antimatter, with matter surviving. And we still don't know what happened to antimatter, and the theoretical models so far cannot explain this asymmetry. But experiments at CERN are working on this. And then all ordinary matter, so all the stars, the planets, and us here, we account for only 5% of the total universe. The rest is dark matter and dark energy. And while we can infer their existence, we still don't know what they are, and again, the theoretical models don't explain them. So to get closer to these answers, we need to keep probing into how particles interact, and that's exactly what we're doing here at CERN. And our tools of choice are particle accelerators and detectors. This is a map of the area. You can see the red star on the bottom is where we are now. And on the right, I have also highlighted the Geneva airport to get a feeling of the scale. And the circles that you see are the accelerators. They work in a chain, and they are connected between them. And the orange triangles are the main detectors. So we start with the hydrogen nucleus. This is passing from a chain of pre-accelerators that gradually increase the speed and the energy of the particles. Then they are injected in both directions inside the Large Hadron Collider. This is our flagship accelerator, where we further increase their energy, and then we make them collide in specific points, right where the detectors are located. And this is where we study what comes out of the collisions. Now, on the left, you can see a part of the LHC itself. It's the largest machine ever built. It's powered by cutting-edge systems, advanced power supplies, machine protection systems, beam diagnostics, and controls. And on the right, you can see the 4 equally impressive detectors. 2 general-purpose detectors, CMS and Atlas. They're designed to capture and analyze everything that comes out of the collisions. And 2 more specialized ones, ALICE, that focuses on very dense collisions of heavy ions, and LHCb, dedicated to studying the asymmetry between matter and antimatter. And at CERN, the internal structure of the organization itself also reflects this setup. So on one side, we have accelerators, which generate and control particle beams, and on the other, we have detectors that study what happens when those beams collide. On the accelerator side, there are several specialized equipment groups. Each one is responsible for different aspects of controlling the beam. So we use magnets to steer and focus particles, radio frequency systems to accelerate them, beam instrumentation to measure and monitor the beam, and kickers for precise injection and extraction out of one machine and inside the next one. And the main focus here is ensuring reliable operation of an extremely complex machine. Going now to the detector side, the goal here is to gather clues from the collisions. So clues that would allow the particle physicists to reconstruct what particles were produced and identify them. And to do this, we use a variety of detector systems. So pixel detectors to track particle paths with high precision, calorimeters to measure energy, and muon detectors to identify specific types of particles like the muons. And while the principles are the same for all the detectors, it's crucial here that each detector independently designs their own system. So this diversity is vital for cross-confirmation of any new discovery. The main challenges for the detector's electronics is handling the enormous amounts of data. So each second, there are about 1 billion collisions. And from that, we need to filter out just 200 most interesting events per second. And these are the ones that are stored and are pushed on for further analysis. And as you can imagine, FPGA development is at the core of both sectors, so both accelerators and detectors. But the focus is different in each case. So in the accelerator community, we are around 100 electronics engineers, mostly working on site here at CERN. And in the diagram, you can see the basic architecture of the accelerator controls for the upcoming run, what we call run 4. So here you can see on the bottom front-end electronics. They're the ones that are close to the machine, and they're controlling and monitoring different accelerator instruments. Front ends communicate through field buses with the back end, and the back end usually processes data from several front ends. And then the back end communicates with the higher layers of servers, databases, and ultimately the applications that the operators handle in the CERN control center. And in the accelerators, we use FPGAs in both the front end and the back end of our systems. So front-end FPGAs are usually housed in custom crates, and sometimes they're located very close to the machine. In this case, they need to be radiation tolerant. Otherwise, they may be placed further away in areas with fewer radiation constraints. And for radiation environments, commercial and off-the-shelf FPGAs are good enough. So we just need radiation tolerant up to 400, 500 grays for the accelerator, so we don't need radiation hardness. And this is why we can use off-the-shelf flash-based like microsemi FPGAs for that. On the back end, we are always outside of radiation, and here we have hosted systems and different form factors. There is VME, PCI Express, PXI Express, and micro TCA. And we design custom FPGA boards in these form factors. And outside radiation, both in the front end and in the back end, we see a lot of Xilinx FPGAs. So the Zinc Ultrascale Plus family in particular is very much used in the upcoming run. And now coming to the field bus between front and back end. For the accelerators, we don't need to handle very high bandwidths. And we have microsecond level synchronization requirements. So in radiation zones, the speeds can be as low as few megabits per second. And that's still good enough for the accelerators. Outside of radiation, there is usually 1 gig Ethernet-based buses, which also support synchronization, like White Rabbit, for example. And overall, as mentioned earlier, the accelerator sector is all about controlling critical equipment. So here, reliability and ease of repair are key. That's why we rely on centrally supported solutions, covering everything from the front-end hardware up to all the software layers. And there is a strong push towards unification and standardization. Coming now to the detector side, things are very different here. The community, first of all, is much larger and more distributed. Here we have hundreds of developers, not only electronics engineers, but also physicists that come from many collaborating institutes. And because of this heterogeneity, we see a wider variety of approaches, including different programming languages, also a high-level synthesis, which is something that has not appeared yet in the accelerator world. When it comes to FPGAs, we have a full range from state-of-the-art Versal devices all the way to more basic microsemi ones. And here, due to the very high radiation constraints on the front end, so close to the machines, FPGAs are not placed at the front end tier. Here is where we mostly find radiation-hard ASICs. And FPGAs are on the back end, so outside of radiation. As for crates, here we have ATCA and PCI Express servers. So they're the ones that are hosting the custom FPGA boards on the back end. And here, between front and back end, unlike the accelerators, where we have field buses, here we have point-to-point links and multi-gigabit ones. So the target, again, of this architecture is to take high volume of data out of the front ends, do some first processing to keep only the interesting ones in the back end, and then send these further for processing at the processor farms and the offline analysis. And overall, in the detector world, there is a lot more experimentation. We see different approaches that are often tested in small scale. And then after a few years, if something is relevant and proves effective, it can be adopted and standardized also for the accelerators. And engineering teams here are naturally diverse in their needs, in their technical expertise, and also in budgets. So there's this inherent heterogeneity that often leads us to take different directions. But there are conscious efforts also to adopt common practices and shared resources in what relates to FPGA design. And I have listed here a few examples, and this is not at all an exhaustive list. Starting with the tools, we now have the EDA committee. It's a new body that oversees the tool selections for the whole of CERN, and it defines the overall strategy for the EDA toolkit. As the user base is growing and as tool options are expanding and also financial constraints are becoming tighter for the organization, this committee helps to ensure that we make coordinated and also sustainable choices. So in the past, for example, programmable logic meant only gates, and you could target in principle different devices and different FPGA families. But with the complexity of today's devices, this becomes more and more impossible. So designs are increasingly tied to specific vendors, and we have to take this into consideration, so the risk of vendor lock-in. Another example comes with simulations. So with the rise of continuous integration tools, a simulation license and the availability of simulation licenses can become a bottleneck. So we are also evaluating the scalability and flexibility here. And so these are some of the topics that the EDA committee is dealing with. Moving on with the technologies, there's the SOC interest group. This has stakeholders from across CERN, both accelerators and experiments, and it will be presented in more detail tomorrow. Taming FPGA transceivers is another area of active work, and there's also a dedicated talk on that. And there are also efforts for common gateway libraries. This is currently under exploration. And finally, on the licensing side, the CERN Open Hardware License, it continues to serve as our common ground for open sourcing designs. There is also the OSPO, the CERN's Open Source Program Office. It supports teams in open sourcing, and not only hardware, but also gateway designs. And leveraging these common assets in this way is critical, and it's a critical springboard to set up the accelerator for future challenges. So with the sheer scale of the future projects, like the Future Circular Collider, this is a proposed collider with a circumference of around 91 kilometers, and you can see it here compared with the LHC. So our ability to work collaboratively will play an even more vital role. So looking ahead, when it comes to controls and electronics of these future accelerators, things are not clear at this point. They are clearer for the detectors, as you can see. But for the accelerators, the current efforts are primarily focused on feasibility of main systems like magnets and RF technologies. So extrapolation to FPGAs is not clear at this point. But there are a few things that we already know. So for instance, our current approach of radiation-tolerant COTS FPGAs at the front end. So this is something that has served us well for the LHC so far. This won't be viable for the future machines. So we will need true radiation hardness, much like what the experiments are doing today. Also, given the scale of future accelerators, we know that we will need seamless redundancy, which means that we will be dealing with many more FPGAs than what we have today. Then our field bus strategy will also need to evolve. We are already seeing cabling limitations in the LHC, and in the future, we will need to share fibers between applications. This is something that we don't do today, and this will imply a lot more transceivers in the FPGAs. And we will also face stricter requirements for precision in synchronization. Today, our requirements are more relaxed, so systems like White Rabbit can rely on FPGA resources. So we can tolerate and we can bypass FPGA limitations with transceivers and with the internal clock distribution inside the FPGA. But in the future, this may not be the case. For the detector side, the ideas and the planning are more advanced. And to tell you more about that, Sophie comes right after me with her presentation. She will give a full overview of the FPGA challenges for the detectors of the future. And this is all from my side. This was just a bird's eye view of what we do. And as you have seen, it covers a wide range of FPGA applications. And we are very happy to have today representation from the accelerators, from the detectors, from other institutes and the industry. And we have put together a program that we think addresses the main interest points and the main pain points of the community. As Davide said, we do encourage technical discussions. So we have allocated generous slots for the talks. So there is time for discussion after the talks. And even if that is not enough, there are coffee breaks and there is the dinner for more exchange. And this is why we also encourage in-person participation. And we also hope our interactions don't finish here. We believe in the value of building a community where we are aware of each other's work, where we don't duplicate efforts, and where we share results. And the vision of this forum is to provide a space for inquiry and for advice and to establish concrete bridges between us and make our individual efforts more fruitful. Final remark talking about the community. So the CERN FPGA community is seeking to grow, and there are currently a bunch of job openings for FPGA developers. I have put the links here, and there will be more to come. And in addition, there are always consultancy opportunities. So let's make the most of it together, and the more we contribute and the more to get to know each other's work, the more we all get out of it. Thank you.